Okay, this is the 15th problem. It's actually Chapter 7, Multiple Choice, Question 24. And it says, draw the molecular orbital diagram that determines the following is paramagnetic. Now, first of all, we want to recognize that we're looking at atoms that are boron, carbon, nitrogen, so they're going to have that odd order in the molecular orbital diagram. So we're going to start with s orbitals in atomic. So these are the atomic orbitals. So when the atoms are far apart, these are what they are, s and p, s and p. So these are the p's. And then they're going to come together to form a bonding interaction. And then they're going to form a destabilizing or anti-bonding. And so there's our zero of energy right across there, right? And if it's above that higher energy, that's destabilizing. That's the sigma star. And then we have the sigma bonding interaction down here. Now the P's are going to come together and form either interactions that look like this. Those are P-type interactions, or they're actually going to be pointed at one another. I can draw them. And that would be a sigma, and that's a pi interaction. Now, it just turns out that for these three atoms, boron, carbon, and nitrogen, the pi are the more stable. And the sigma, so that's the P sigma, this is the P pi, and then there's going to be destabilizing, and this order doesn't change no matter what the atoms are up here. That this is the sigma star that comes from the P, and this is the P pi antibonding. Okay? So now we're going to take the number of electrons in each of these, and we're going to put them in to the atomic orbitals and then actually the molecular orbitals. So our first option here, I'm going to start at the bottom and go with boron, B2. So I'm down here, looking at this one, right? Boron and B2. Boron is in group 3A, so it has 3 each. There are 2 of them, so there's a total of 6 electrons. It's the neutral. So for boron, we're going to put a total, so boron, 6 electrons, and it's going to go 2, 4, 6. See, because of that is the pi interaction, they have to go into individual orbitals first, and then they'll pair up on the second time. So indeed, right there, that shows an unpaired spin, and that is what gives rise to paramagnetism. And that means that's the correct answer. Let's just check the others. B2 minus, so if we were going to do B, and this is B2, of course, that's B2, and that's 2 minus, that would be 6 plus 2 more, because it's 2 minus, 8 electrons. And those next 2 then, see, go in to fill those guys up. And it takes away the unpaired electrons. That is not going to be paramagnetic. Next one is B2 plus, or 2 plus. Neutral has 6 electrons. This is going to have 4 electrons. So 2, 4, those are not there. They're not there. And so we're going to have no unpaired electrons, so not paramagnetic. C2 minus, C2, 2 minus. The C2, carbon, has 4 electrons in the valence shell. There's 2 of them, so 8 electrons plus 2 from the negative charge. That's going to be a total of 8 plus 2 is 10. 2, 4, 6, 8, 10, not paired. I mean, they're all paired. And then the same true as N2, 2 plus. You can put those in there. N2, or N, has 7 electrons, 2 of them, 14. It's 2 plus, that's going to be 12. So it's 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. Nitrogen has 5 times 10 is 2 plus. So nitrogen 2 plus only has 8 electrons. 2, 4, 6, 8. And it's going to be staying down there then. But all are paired up, and therefore they are not paramagnetic. The only one that's showing spins, unpaired spins, are paramagnetic B2.